Thanks for the invitation. In today's talk, I'll be very happy to share one piece of our recent work, which was just accepted at iClear 2026. In this paper, we are tackling the missing value imputation problem, and we try to tackle this problem from the neuro-symbolic perspective. This is a piece of work, this is a joint work with some of my wonderful students. Wendy is the first author. She's here today. She will later help with some questions about the experiments. And also we have another two wonderful students. They just graduated and joined some top PhD programs in US, like the UVA and the TMU. Okay, Wendy, we can go to the next slide. Okay, first of all, I want to talk about the problem we want to tackle. As shown on this slide, we have a snapshot of some data collected in healthcare. You see that on this is a tabular data, but we can have we see many missing values. So missingness is a very common issue in healthcare. Some of the missing values because some measurements are infeasible to collect, and some of features may be unnecessary to collect. But imagine if we pass this type of data with many missings to some machine learning models, then of course the missing values will hurt the performance of the machine learning models. For example, suppose we want to design the model to do the prediction or to the classification. So in real life, in practice, usually we need to first pre-process the data to improve the data quality. So this is how the missing imputation involved. We want to design some machine learning algorithm to first impute the missing values. And okay, so Wendy, you can go to the next slide, right? How to impute missing values is a classical problem in machine learning. Here, I have listed 4 branches of commonly used methods. For example, we can start from talking about the statistical approaches. So imagine we can use the observed data to infer the missing values. Suppose we can capture the correlations between those variables, then given the observed values, we can leverage, for example, the correlation and build the estimate the conditional probability. Then we can predict the missing ones. So this is from some classical statistical point of view. And nowadays we have some neural network models. You can imagine we can build the neural network models to treat the observed values as input and use a neural network to output the missing ones. For example, we can use a multi-layer perception model, or we can use some deterministic autoencoder model to first map the observations to some latent state, and then using the latent state information to produce the missing ones. And of course, nowadays we have many powerful generative models. Intuitively, generative models will be a very good tool in this scenario. For example, we can have VAE-based general model, or GAN-based, diffusion-based, or normalizing flow-based. Given those general models, we can generate some data that can mimic the distribution of the target distribution. But the drawback here is usually to train a very good general model, we need to, this is very data demanding, which means we need a huge amount of data to train the generative model. And also, their data generating mechanism can be treated as some black box, which means we cannot control the generating process. And for example, maybe we want the generated data to satisfy some domain constraints, then these domain constraints will be very hard to be fused in this generating procedure. So this is the potential some drawback of the general models. And then people may think we can build a transparent model instead. For example, we can build some rule-based models. Then given the input data, we may build some rule-based model to produce the output. But in this along this branch of research, most of the existing tools are only working on the observed data. So usually those rules are built based on the fully observed samples. And in this paper, we actually propose a different view to tackle this missing value imputation problem. So the high-level idea is we treat those hidden values as some latent states, and we want to first use the neuro-symbolic tools to perform the reasoning. In other words, we want to first reason about those hidden facts by some multi-hop reasoning. And then the reasoned results will be used as new evidence to get the rule learning. So this on this page of slide, this figure illustrates better the differences of existing approaches and ours. I think from the high-level perspective, our proposed approach, shares some similar flavor with the EM algorithm. So EM algorithm is a classical algorithm that can handle the missing values. So for EM algorithm, they just treat the missing values as a latent state. Recall that for EM, they alternate between E step and M step. So for E step, they are using the observed data to infer the posterior distribution of the latent ones. And for the M step, they are use the inferred results, build some surrogate of the log likelihood function, and M step is about model learning. So from this perspective, I think our approach shares some similarity with the EM algorithm. So our algorithm also alternates between the inference and the model learning. But for the inference part, we are using the neuro-symbolic idea. Basically, this inference is guided by the current learned logic rules. So we are using the rules to get the reasoning, to reason about the latent parts. And also we have some model learning parts. This is very similar to the M step. And in the model learning, we are actually learn the rule content. So you can see that our approach alternates between the inference and the rule learning. So the output will be the learned rules that can explain the data generating process, and also given the rules, we can impute the missing values. And also because the data is imputed by the rules, so we are trying to impute the missing values in a more controllable and more safe way. So this is the benefits brought about by the rules, right? So as a summary, so our algorithm will alternate between rule discovery and imputation. Next slide. Next slide. And you can imagine that better rules will lead to better imputations, and better imputation results will provide better evidence for learning the rules. Okay, next slide. Yes. Okay. So first, let's look at some example of the input data of our algorithm. As shown on the left, we can see tabular data. It contains a bunch of features, and the features in this. We start from a very simple scenario where we assume that the features are all binary data, either 0 and 1. So you can treat the observed features as some observed facts. But in this table, we also have some missing values. So you can think these missing values can be treated as some to be discovered facts or unknown facts. And behind the data, we assume that there exists some logic rules that can be used to explain the data generating procedure. For example, as shown on the left, you can imagine, although some of the values of the x3, x4, and x5 are missing, But suppose we know such a tree. Then, given the evidence from the x1 and x0, given this evidence, then we can then we can use evidence to deduce the state of x3. And also, if we know the evidence from x3 and x7, and all those input evidence will be used to deduce x4. And given the inferred states of x3 and x4, combining with the evidence from x6, put everything together, we can continue to infer the state of x5. So you see that in this, in our paper, we are using this rule-based inference scheme to reason about the missing values in this data. We just treat the missing ones as latent predicates, and we are using these rules to discover those facts, and those discovered new facts will be in turn used in the process of rule learning. Okay, yeah, so the overall framework will be alternating between differentiable forward inference. So I will talk about we will use the rule to do the reasoning. More specifically, we will design some differentiable forward training inference. So everything is working in the embedding space. So the reasoning, all those operators are differentiable operators. And then yes, the alternate between the inference and learning, we can get our final outputs. So in this figure, it illustrates the overall framework of our method. Although the picture here is a little bit complicated, but I just want to emphasize one message. So everything is now represented as embedding vectors. The predicate is embedding vectors, and the rule is also represented as the embeddings. So we are working on the embedding space. And the forward reasoning is realized by some differentiable Neuro-Symbolic based operation. And on the left, we show the diagram about the forward reasoning operation. And on the right, it is about the learning pipeline. So you can see that actually the learning is quite challenging. Actually, in this paper, we have designed some optimization pipeline to enable the learning to make the learning procedure complicated, realized in a more tractable, feasible, and efficient way. Next page. Right. So let's first talk about the forward reasoning. So in this paper, we consider the rule of such a form. It contains two parts: the body predicate parts and the head predicate parts. So given this rule, so you can imagine, suppose from the evidence the body predicates become true, then we see that this rule will be activated. Then we can use the body condition to imply or to deduce the head part. We can look at a concrete example. For example, if you have observed the floor is wet, and you see the umbrellas, those are some evidence. Given those evidence, you can deduce that maybe it is raining outside. Even though maybe whether it's raining or not, it's unknown to you, but you can still use evidence to make a guess. So this is about one hop or reasoning. So we are using this rule-based inference to reason about the unknown facts. Next page or slide. Next slide. Oh, right. So, and this page of slide illustrates why multi-hop reasoning is better. So, in fact, in this paper, we are using the multi-hop reasoning scheme to reason about the unknown facts. So, why multi-hop is better? For example, as shown in this example, we have two rules. Suppose x3 and x5 are unknown, but you can get access to the evidence from x0 and x1, and given those evidence, you can deduce x3. And the deduced x3 will be served as new evidence, so will be combined with the x6 to deduce the x5. So you can see that in this example, to deduce the x5, you need to go through two hops. So basically, the evidence will propagate it over those series of rules. And for example, and you can, so this example illustrates that we need to use some multi-hop reasoning scheme to arrive at to discover some facts. And in this process, you can see that the current facts, we denote current facts as some vector called V0. So you can see that you can imagine many elements of the V0 vectors will be missing, but some of them are observed. But we want to use the rule-based reasoning to perform such a step-by-step forward training to arrive at the deduced results. So you can think that in this training process, we recursively update such a V vector. So you can treat the V vector as some state. So we progressively update the state by the forward reasoning. So here we want it can convert to some level after the total number of T hops reasoning. Okay, next slide. Next. Right. So next, let's take a closer look at our forward reasoning model. I have mentioned everything is working on the embedding space. As shown in this figure, so the predicate is represented as embedding vectors, but they are anchored or they are fixed. As shown in this figure, we are using the one-hot embedding vectors. But in one of our recent work, we actually can pre-train those embedding vectors. For example, you can extract the embedding vectors from the shallow layers of LLMs, and then using some PC algorithm to reduce dimensionality of the embedding vectors, and you can treat those low-dimensional projected embedding vectors as our predicate embedding here. But the takeaway is all those predicate embeddings will be fixed in our training procedure, and our model parameters will be the rule embedding vectors as shown here. Theta is our rule embedding vectors, because we know that in our setup, the rules are unknown, so we want to jointly learn the rules. So you can think learning the rule procedure can be translated as we select some of the predicate embeddings to fill in the slots of the rule embedding. So this selection procedure itself is non-differentiable. So in fact, here we are using a trick. We are computing some similarity score. Basically, we want to convert the selection procedure by computing some similarity score. These similarity scores will be used to select the relevant predicate embedding to fill in the rule slots. And this will make the selection procedure differentiable. And given the selected predicates, now you can imagine that we will know the content of the rules. Given the content rules, given the observed facts, then we can apply the multi-hop reasoning. So this is realized by a series of soft-min and soft-max functions. So the soft-min and soft-max will be some soft approximation of the all function, and function and all function, because we want to check whether conditions of the clause is true or not. So this checking usually involves a lot of and all operations, but those operators, these symbolic operators, are non-differentiable. So we replace these operators by some soft-min and soft-max, make all those operations differentiable. Okay, next page or slide. Okay, written all those things in a mathematical way. So you see that theta f is our model parameters. It's about the rule embedding. So first, we apply the cosine similarity to help us select the relevant predicate to fill in the rule slots. Once we have selected the predicate, now the rule slots will be filled in, and we know the content. So you see in the bottom, this equation illustrates the one hop reasoning. So given the current model parameter theta encodes the root content, and given the current induced V encodes the current evidence, current induced facts and the known facts, and we will use the current facts and the rule to do the one hop reasoning. So the output of the G is you can imagine is the deduced new effects. But here we are introducing some mask M, because the introduction of the mask is to make sure that if some facts are already observed in the data, then we do not need to update in this forward reasoning procedure. So we will use a mask to indicate this. But for some unknown missing parts, we need to infer using this multi-hop reasoning, and we will use a mask to indicate which part needs to be improved, it needs to be updated, which part will need to be unchanged. So this equation illustrates the one-hop reasoning. We'll apply this equation recursively, so this will mimic the multi-hop reasoning until you can imagine the V-vector convergence. But in practice, we do not want the reasoning steps to be that long. From the empirical studies, we can set the total number of reasoning steps as 3 or 4. That would be a reasonable number in our experiment. We also tried to adopt some adaptive way to determine the number of reasoning steps. But from the empirical results, we found out that setting the reasoning steps at 3 or 4 will be a good number in our experiment. Okay, next page slide. So here are the functional formula for the soft min and the soft max. As mentioned, they are soft approximation of the and or operators. And you see that to use those approximation functions, we actually additionally introduce some tuning parameter tau. Tau is called temperature. So you can see that the value of tau controls how precise are those approximation functions. And so you can imagine that tau is a very critical tuning parameters in learning. So in practice, we investigated, we can use the annealing algorithm to adaptively tune the values of tau to in the learning procedure. Okay, so that next page slide. Okay, so so far we have discussed we make the forward training differentiable, and by applying this multi-hop reasoning, then we can get we can arrive at the deduced factor vector. And then the loss is built on the deduced facts with true observed values. But in our data set, for these missing values, we do not know the true observed values. So this loss is built based on the true observed values, but combined with some mask techniques. So you can think that for those observed values, we intentionally introduce some mask out some values, pretend that those parts are also missing. And the loss function is built based on comparing the deduced facts with the observed ones to form the reconstruction loss. By minimizing the loss, we want to learn the model parameters in a differentiable way. But I want to emphasize here is although the loss is built based on the masked values, but you can imagine all those missing values have been inferred in this process, because the final value used in the loss will also depends on the induced effects of the missing ones. So in summary, so all those missing values have been inferred in this process, and those will be served as some evidence to construct the reconstruction loss. Okay, next page slide. And also I want to okay, so now next let's talk about the model learning. actually our model is the learning is a challenging problem because it is a combinatorial optimization problem by nature, and more specifically, the rules considered in our paper can have a very complicated form, which means it can be of the disjunctions of conjunctions, which means that they can be the of ends. So you can think that because the underlying rule structures can be quite complicated, so it will be very difficult to learn all those model parameters in an accurate and efficient way. So actually, in our paper, we design some optimization pipeline. So the idea is we do not want to update all those parameters simultaneously. We are using some staged optimization procedure. Okay, next page slide. Okay, so here we from the high level idea, so this page slide illustrates the overall optimization pipeline. So as we mentioned, the learning problem is a very challenging problem in our model, and actually we are adopting 3 different types of techniques to in learning. The first technique is very similar to the coordinate gradient descent algorithm. So if you are familiar with the coordinate gradient descent algorithm, it's about if you have a high dimensional model parameters, instead of updating those model parameters using gradient descent, you every time for the coordinate gradient descent algorithm, each iteration you just choose one component to update and treat all the other remaining components unchanged. So we get inspiration here. So basically we developed we decompose our rule model parameters into different blocks. So you can theta k. You can see here theta k is one block of rule parameters. And theta k is about the rule content associated with the predicate k. So we are using this block coordinate gradient descent version, which means every time we just focus on theta k and treat the other model parameters unchanged. So once we have learned theta k to converge, then we will move on to the next block. So we are updating the rule parameters at the block level and in an alternating way. So this is the first strategy we used. Second strategy is about how to deal with learning the all of ends type of rules. So even though we can focus every time we can focus on one block of model parameters, but if the rules is represented as the all of ends, so it's very hard to discover all those ends part. So this is a challenging problem. It's by design, by the complexity of the rules. Usually, the strongest rule is easy to discover, but for some weaker rules, some low frequency rules, it will become harder to discover. So to drive our model to discover all those diverse rules, we are using a classical algorithm called a sequential covering algorithm. So the idea is pretty intuitive, which means we first focus on learning one rule and one end part. Once we have learned this part, we will go through all those samples to check which samples have already been explained by the discovered rules. And then we'll remove those samples from the data set. And in this way, we drive the model to discover new rules from the remaining data set. So the sequential covering is we sequentially learn the rules one by one by removing the samples from the data until all the samples have been deleted. Then this means we have discovered all those diverse rules to cover all those samples. But in our algorithm, this is not over yet. And we still have a fine-tuning tuning stage, which means in the end, once we have discovered all candidate rules, we will pull all those rules together, and this time we will treat all those rule parameters as the entire parameters, and then we'll, because the of ends we have replaced this all operator using the soft OR, and you can see that you can imagine that now we can use the gradient descent algorithm to fine tune the model parameters. So you see that actually we are adopting 3 strategies: the block version of gradient descent, sequential covering to pick up the rings to learn the rules one by one, and the final fine-tuning because we are working on the embedding space. All rules are embeddings, so we can fine-tune those embeddings in a differentiable way by gradient descent. Okay, next page slide. Next. Okay, and I also want to highlight that although in all our previous examples we are dealing with binary features, but in our paper we also proposed some ideas about how to handle continuous features. So the idea is that we will design some soft predicates which can convert the continuous features to some predicate. But this predicate invention has learnable model parameters. For example, we know that some predicate may be related to the blood pressure, but how to define high blood pressure, low blood pressure, we need to learn some threshold. And all those thresholds will be treated as learnable model parameters. So all those parameters will be learned together with the rule embedding parameters. Okay, okay, next. Okay, next, let's go to the experiment parts. So I want to start with the synthetic experiments, as shown in this slide. We consider 3 cases. So you see that we designed 3 different types of rule structures. For the first case, it's a very simple chain-like rules. And for the second case, you see that the last x5 is a disjunction of conjunctions. So you see that to deduce x5, basically we have to because it's represented in the all of ends. So you see that you can imagine that to discover those rules will be a more challenging problem. So the case 3 will be even more challenging. So you see that we considered 3 cases with the increasing difficulty levels, and for all those 3 specified rules, we generated the synthetic data given these rules, and we create some data with missing values, and we want to evaluate whether our proposed model can impute missing.
So let's continue about the experiment result. So just as we see, we have 3 sightings about the synthetic data, and this experiment result is the example B. Yeah, just this example, and we just show one example, and all the other experiment results can be found in our paper. So this is example B, and we give the observation ratio with 0.2. It means we have missing about 18% data, right? So we want to impute such 18% data, and we can only see about 20 of the data. And for this trend, they are viewed as the known fact. Okay, so we want to make the imputation the other part. So we can see the result for the simple rule about x3 and x4. For 3 and x4, they are from just one chain, right? So it will be very simple, and our method can learn the perfect result. So it gives the 100% imputation accuracy, and the learned rules are exactly correct for these 2 parts. And for the x5, it is end of rule. So this is x5. So we have 2 chains, right? So this is all end. So the result is not as good as X3 and X4, but it's still acceptable. So we can see the imputation accuracy after fine-tuning is about 95%. So it is still very good. And for the learned rules, as we run several times with different seeds, and for example, for here, if we run 20 seeds, and for the rule accuracy, it means about 50% of the seeds can give us the correct rule. So that means rule accuracy. So for example, we run 20 or 30 rounds, 20 or 30 seeds, and how many of them will give us the correct rules. So we can see the top 3 rules learned from different seeds, and the top 1 rules are the correct ground truth rules. So our methods still work well for this hard X5. And this application study shows why the fine-tuning is useful, because this is from one seed from our run. You can see before fine-tuning, this X0 and X2, this part are wrong. And after fine-tuning, this part goes correct. Yeah, so that is why our fine-tuning is useful, because you can see in some n of all rules, it means we have multiple chains. And if we only have one chain, if it is correct, it will give some potential correct result. And so after fine-tuning, we'll get the totally correct this structure. So that is an application study about how our fine-tuning works. And we can see this figure, and it will give a more clear description of that. So we can see, before our method is the staged or the blocked coordinate descent. So it means we optimize the rule embedding one by one. So you can see, assume for the first 20 epochs, we optimize the rule for X3. So you can see for the X3 and this blue line. So the accuracy becomes it very quickly becomes to 100%. And the training loss still is decreased very quickly and going to the optimal stage. So that is in the first 20 epochs, we optimize X3, and then we go to the optimize X4. Again, it's very, very quickly, it goes to 100%, and the training loss just decrease. And now we go to the hard case for X5. You can see X5. Firstly, the training loss, and it goes to some suboptimal stage. This part is not optimal, because our accuracy, you can see our observed accuracy is not 100%. So in this stage, it's not good enough, and now we need to stage. So this D and the E are only for X5, and this is a fine-tuning stage. So we can say after fine-tuning, the accuracy goes to the 100, the fine-tune loss, blah, blah, and it's go about 0. So it's going to the optimal stage. So that is the case. So the remaining samples means when we train the X5, we would sequential covering. So it means here here samples are all the same, and update is just decreased because some of the samples are correctly covered by the learned rules, and if they are covered by the learned rules, and then we just delete them, so it will just give us a very, very quick decrease. So that is how the sequential covering works for our method. So that is our whole for example. And you can see this our method can exactly learn the simple rules for X3 and X4, and also very effective for the offhand structures for the X5. And another issue we want to mention that you may be concerned about the training order. because we mentioned we will have a cycle or a sequential, like maybe we for the same example, for the example B, we need to train the rules for x3, x4, and x5. So the training stage is important. Maybe you may think the training stage is important, but actually the training stage is you can start from any order. So the training order random. For example, this is one example. So this is round 1 for some seed, and round 2 for another seed, and then round 3 for another seed. So for example, you see round 1, if we first optimize x5, so it will give us, so x5 cannot be correct because we don't have the correct x3, x4. So because x5 is based on x3 and x4, so if we first train x5, it will be wrong, right? And our method will just try any other random order, and after some order, it will because finally we will have x3 and x4 correct, then x5 will be correct. So you can see round 2, round 3. If the round 3 is just an example I show. So if we train in the greatest order x3, x4, x5, it will quickly give us the correct result. So in this table, I just want to mention the optimization order doesn't affect for our method. You can start from any random order and try enough times. After you try enough times, you will find the optimal stage, and we will get the correct rules. So this order doesn't affect. And this one is also, I just want to mention what is the convergence analysis for our training dynamics. So still actually they are the same. So you can see this is cycle 1 is for start from x5, and this cycle 1 will start from x5. So we need to try sometimes, and then after we train x3 and x4 correct, then we can have x5 correct. So I think I want to talk. So this figures fully support this result from our table. So they are the same. Okay. So another result is from some real-world data set. So we have 3 real-world data sets, and the first is a bird. So it's a very dark, and it is for interpretable logic recovery. So in the ground truth, it has several rules about that. So that's the ground truth rules. And we just select 2 targets as our missing target. They are abnormal bird, this target, and can fly, so this target. So we mix these 2 targets, we randomly give some missing. For example, we give 19% of the missing. So it means we only observe 10% of them. And then we want to recover these 2 predicates. And we also we want to recover the rules, the ground truth rules. So that is our result. And you can see our model can perfectly recover the rules and also give the perfect imputation accuracy. And compared with other interpretable baselines, our model can work best. You can see other models, and they cannot give the exactly correct rules for this data set. Okay, but they can all give the rules because they are interpretable rule-based baseline. And another data set is about healthcare, because we know in healthcare missing value are very important, right? So in this heart disease data set, we still have several features from the patient. For example, we have more than 20 features from the patient, and we select 4 of them as our missing target. And for this missing target, then we want to learn the rule to interpret them. But the key here is that we don't know the ground truth. In the bird, we can see we have the ground truth, so we know what are the correct rules. But in this medical data set, we don't have the ground truth. So we just ask doctors and ask large language models whether our rules are meaningful. So if so, they said these rules are very meaningful, and to give some medical meaningful rules and try to predict them, predict this missing target. So in this case, these features are continuous features. So we can see the learned rules have some threshold. For example, if age is more than 16, and it will have high risk to get this trait BPS high. So our learned rules have some threshold, and that is how we can handle the continuous features. And compared with other rule-based baselines, they cannot handle these continuous features. They can only handle binary predicate, right? So our result will be better than this rule-based baselines because we can handle the continuous features, and it will be more correct. Okay. And another is that after we also compare with the black method as we introduced before, for example, for VAE or for diffusion or for again. So these are some black box imputation. And we can see in some cases, black box will get a higher accuracy. So that is meaningful, right? Because black box for this training, I think that these talks are not very difficult for this black box model, but you can see our method is comparable. The strongest black box baselines. So the gap is very, very small. It's just about 1%, right? So it means this our method can give the competitive result with the black box baseline, and we can also have some. We can also give the meaningful rules, which are very important in some domains like healthcare. So interpretability is our a key advantage compared with this black box imputation method. So another result is about the downstream task. It means after we have the missing value, we have imputes these missing values, and now we can do some downstream tasks. For example, we can do the diagnosis prediction for heart disease. So for heart disease, we will predict the final diagnosis, whether they have the heart disease or not. So that is after we give the entries, we give the values for the missing features, and with our predict missing features, now we can give the diagnosis result for the final prediction. So that is the accuracy result and F1 result compared with other baselines. So we can say our model still gets the best result. Okay, so it means this predicate, this missing value imputation is also important, is also useful, and for this downstream task. So that is all the results, and other results can be found in our paper. And for give a summary, it means our method formulates missing value imputation as a joint latent predicated inference and rule discovery. So this is our key novelty, and it combines differentiable forward training, black coordinate optimization, and weak supervision on the observed entries. So the method is also can support both interpretable rule coverage and competitive imputation accuracy on synthetic and real-world data set. So it also can handle continuous features, right? So the final takeaway is that we want to see missing value imputation can be treated as a reasoning problem. So recovery incomplete data while revealing the hidden symbolic structure behind it. So our final takeaway will be that, and this is our key novelty. So we make these two problems together. And that's all for our presentation, and thank you very much. And we are very, very sorry about the internet issue again, and we are welcome to any questions.
Great. Thank you so much, Wendy and Shuang.